Good afternoon. Thank you, Chen. I'm Liang Cai. You can call me Kevin. I'm from Canon Medical. It's my honor to be here, and thank you for the invitation. And for all the audience, thank you for staying late on Saturday afternoon. I hope you will enjoy some of the images here. So today, my title of the talk is AI for CT reconstruction, image denoising, and beyond. Okay. Yeah. So before I talk about these slides, and I'd like to share with you a story. So during yesterday's reception, I was having some very interesting discussions with some of the colleagues here, and particularly once we discussed a lot on how we are fascinated about ChatGPT and GPT-4, basically as an AI, how it can help us, how it impact our life now. And we can feel that in daily life even. So you can use that to solve math problems, writing code, and help you revise your PowerPoints maybe next time. And on the other side, we also talk about nowadays, especially in academia, like students are more and more interested to do deep learning based stuff. They want to do deep learning for everything. So it doesn't mean AI and CT reconstruction, they fuse together, but from these conversations, just like the pictures here showed, I think it's the fact that we definitely see a lot of overlaps between AI and CT reconstruction. In particularly like low-dose CT, including denoising, resolution enhancement, artifacts reduction, workflow improvement, and so on. So yeah, before I jump to the main content of this presentation, I'd like to briefly share with you Canon's the highlights of CT and deep learning reconstruction development. So on the bottom side is you can see it's more like the hardware breakthrough. So it's the first wide coverage CT, and then the first ultra high resolution CT launched in 2011 and 2017. And on the top, you can see like the evolution of different reconstruction algorithms from hybrid IR to model-based reconstruction, and then to deep learning. Okay. So then, yeah, in today's talk, I'd like to mainly talk about several stuff. First is the AI for CT denoising. So we talk about denoising a lot in this workshop, and a lot of very interesting topics. And then I'll share with you so-called Peak. It's another Canon product. It's one step forward. And after that, I would like to do a brief technology review. So what we have learned, and hopefully everyone can get something. And in the end, I will briefly share with you two additional examples leveraging CT's, leveraging AI's advantage. Yeah, as I showed in the previous slide, we've been developing deep learning reconstruction from 2018, and this is our first product called AIC, the Advanced Intelligent Clear IQ Engine. So yeah, this is not fancy, but very powerful. So the input is high noise APP-like reconstructions, and the target is MBIR-based images. So the reason we choose MBIR is we believe that using this, I mean, it includes all these optics models, physics models, and using that as target, so we get for denoising, at the same time get the resolution benefits from that. So in this slides, you can appreciate how the image quality improves. From the very left is the FPP, and in the middle is the 803D, so which is Canon's hybrid IR hybrid iterative reconstruction method, and on the right is the deep learning reconstruction, and you can see very obviously the reduced noise, and the grain size is finer, the noise texture is nature, and it also looks sharper. Okay, Yeah, so here I just would like to share with you some clinical examples. So in this particular case, it's on the very left, it's a normal dose cardiac scan, and in the middle is and the right is 20% dose, but the reconstructed with different algorithms, basically the hybrid IR and deep learning. So you can definitely see in the very right one, so it has a very good denoising, and image quality-wise, it's definitely way better than the middle one. And I'm not trying to say that we can do 20% dose for every scan, but this is definitely possible for some of the cases. And there's still debate in the industry and also in the like a clinical world. So what exactly is the dose reduction? I think that's a very complicated question. So I just cannot quote one single number, but it's just shows like how powerful it is even in clinical examples, and these are all reviewed by doctors. So this is the CPR images. And this is another example to show how, in clinical world, we can benefit from this algorithm. This is for pediatric patient. So of course, like kids cares about, they want low dose, right? And you can see the difference between the conventional ADA reconstruction and the deep learning reconstruction image quality difference. And here's another example, show the 4D CT, so also for cardiac, and this is reconstructed with different reconstruction algorithms. And the point here is, even you see this in the 4D manner, so you don't see, for example, if the deep learning reconstruction itself is not robust and not consistent, then you will see, for example, some so image appearance difference from frame to frame or from time to time. You will see just not as natural, but here you can clearly appreciate the image quality. And I also want to share with you a few more examples based on equivalent precision. Sorry, like this, you cannot see the title here. And maybe you can see from the images, like the resolution-wise comparing the previous images is better. So these images are based on Canon's high-resolution CT scanner. So and the deep learning reconstruction is also applied on that, and we developed for different body parts. From a vendor point of view, so we want to develop this thing. It's not just to look great, and you also need to consider for different clinical applications of different organ or different anatomy. So what doctor really cares about? You want to emphasize the resolution, you want to emphasize the low contrast detectability, things like that. So we need to tailor our algorithm for the particular applications. Yeah, this is an example for the branch duct IPMN case, and you can see in the pancreatic these IPMN and also like these features, the excellent noise reduction in the resolution can definitely help the diagnosis. And this is another body example, so you can see the deep learning reconstruction improve the small structural visibility in the liver, and for both like hypodense and hypodense structures. Okay, so okay, doesn't work. Okay, anyway, so yeah, before I move to next slide, I'd like to pause a little bit and want to take another look of what I just mentioned, the equivalent precision, so which is Canon's high resolution CT. So the difference between that one comparing to conventional CT is mainly there's different folds, but one of the most important part is from the detector side. Basically, like the pixel size is 1/2, and so in the isocenter, it's the size is a 1/4 millimeter size, and the channel direction basically got doubled. So with that, you can, it's very obvious, right? So you have a higher resolution detectors, and also we have more precise X-ray tubes. So the purpose is to get high resolution. And I also showed some examples before. So we also have deep learning reconstruction developed for that. So then an actual thing we thought about is, can we do something one step forward? So this is then it's lead to this one. It's called the Precise IQ Engine. The product name is Peak. So this is our first super resolution based deep learning reconstruction algorithm. And this training process is we have data from the high resolution precision scanner, and we can downsample that to, we have the in-house simulation tools. We can do the downsample and get the downsampled input, so which can get our normal resolution CT like images. And then also we have the fully like geometrically aligned high quality training target. So based on that, we train a 3D neural network to do the noise reduction, and also more importantly, the resolution enhancement. Okay, yeah, here's some examples. So this is an example with this patient has the plaque in the cardiovascular vessel with strong calcification, and you can see the difference between the atrial reconstruction on the left side and the peak on the right side. So you can see that the calcium blooming is significantly reduced, and doctors can see the stenosis much more clearly. Here's another example. Also try to demonstrate the resolution benefit of the peak. So you can see this small vessel here. So here it's more or less look like noise, and so in the peak reconstruction, you can see that very clearly. Yeah, it's much better visualized. Okay. Yeah, so this slide I want to demonstrate that for this super resolution deep learning reconstruction, we use the 3D network instead of a 2D network. We used for our first generation denoising algorithm. And I'd like to use example to demonstrate the benefit of that. So on the very left, it's the APP recount. So you can barely see this. I put these arrows here so you can see that there's two small vessels. You may also think that's noise. Yeah, if you're using conventional 2D denoising, so the noise got suppressed a lot, and but the signal is also more or less blurred, and you can see that maybe a little bit better than the left one, but not very clear. And on the very right is how the super resolution based deep learning reconstruction did, and you can clearly see that vessels, because the network is a 3D, so you can have a stronger power to capture these features. It's not just to look at the features in this 2D space. You can you're extracting information in the 3D space. And you can also see this aortic valves is also like much sharper comparing to conventional deep learning reconstruction. Okay, yeah. So I've showed a lot of nice images here in our first and the second generation deep learning reconstructions. They are not just for AI denoising, like for the peak, it's denoising and also have the resolution enhancement. Basically, we try to maximize the system's resolution through this algorithm. So here I'd like to just pause a little bit to summarize, like in the world of AI denoising, like what's happening and what we have learned from this. Basically, some takeaways. First is the training data and the training scheme or mechanism, whatever you say, considerations. So this is sounds silly or simple, but I think this also is one of the most important things. So all the AI algorithm is data hungry. So people always say garbage in, garbage out, right? There's so many different ways to prepare your training. You have various training pair selections. You can use different training target. You can have different ways of formulating that. You can do, say, like low dose to high dose. You can do noise to noise. You can do thin slice to thick slice. There's a lot of different choices. So, and how do you make that selection? And there's also different schemes. You can do indirect, so basically image domain processing. You can do direct reconstruction, and you can do hybrid. Yeah. Also, second is network structures, and so nowadays, I mean, people use CNN a lot, and in the near future, or I don't know, so like there's, I mean, all these new structures continues to popping out, and examples including not mentioning GAN, but like MLP, transformer, a lot of new stuff is popping out from time to time, and so how we adapt that in the future, and whether that's really helpful is just a fancy, and especially for CT denoising. And yeah, also we have 2D and 3D networks. And of course, you can have 4D, 5D even, depends on applications. Yeah, the third part is the image quality control. So this part is, yeah, I'd like to pin down to the loss function design. It's like you can have a denoised image, but it's just a beautiful image good enough. And what is your target? What is your imaging task? And how can you design, for example, certain schematics, or especially, let's say, the loss functions to achieve that target? And there's different studies in this community. So, for example, people using weighted loss of like bias and variance, like in the web team, and people also did, for example, they can try to put different filtering for the input and the target. Depend that you can do the mixed frequency training. Of course, like the robustness and interpretability is the important part. So we heard a lot of talks in this workshop on that. The uncertainty estimation, there's different ways to do that. Here I just listed one example, but doesn't mean only that one. And of course, there's a lot of new research directions popping up, including the new AI models, technologies, especially the generative models like DDPM, and there's other ways. And also like in the future, big data, clinical data construction, like G1 mentioned, and much more to come. Okay, yeah, so what I want to say, summarize here is, this is an active research field for several years, and from vendor point of view, Canon is one of the vendor actively developing that, and so GE and Philips also have product on that. Yeah, so here I just want to summarize. This is sounds simple task, but really, if you want to do that well, and like a doctor can trust that, it's not an easy thing. So we need to work together on that with the entire community. So in the end, I'd like to briefly share with you two additional examples leveraging AI's advantage. The first one is AI for long motion correction. So in Canon, we developed the algorithm, tried to do the motion correction for the entire long scale. It's a helical reconstruction. So the way we do that is we get the raw data, and we try to do the partial reconstruction and get the images, so-called parse, and using that to go through the DCN network and get the motion field, and then to do the motion compensated reconstructions. So here's just a little bit more details on that. So in the helical scan, you can try to get the data range, like basically back-to-back data range. And this is what we are doing, and that doesn't mean this is the only way to do that. And so you can get the high images from back-to-back and you need to select a certain data range, and then you can using the neural network to get the motion field, which is not new, by incorporating that to the reconstruction process, you can get the motion crafted image. And I'd like to say this method itself is why we're using deep learning. There's other ways you can using image registration, for example. But here, basically, we really want to leverage AI's advantage in like fast inferencing, so you can get the images quickly. Yeah, here's just some examples, like I'll quickly fly through. So you can see before and after motion correction. Yeah, this is just to try to show in the Z directions. So basically, it's not just correct for single image, but the entire volume. Anyway, this has some problems. I just skip for time consideration. Oh, sorry. Okay, yeah, in the end, very briefly, on another application for cardiac motion correction, similarly, we try to leverage AI's advantage in object localization and the segmentation, and also the motion field estimation. So for cardiac scan, it's although in the past decade, the scanner getting faster and faster, but still you cannot freeze the heart. I mean, physically freeze the heart. So motion correction is always something people need, and so we are developing AI-based algorithm to do that. And just quickly show you some examples. So this is for before and after motion correction. This is for different vessels, the right coronary artery and the LAD from the right side and left side. And you can see before and after motion correction results. And I'll emphasize here is this is not just to seem good in one like actual slice. It's basically it's for the entire vessel. So you can see after motion correction for the entire vessel, how the image quality changes from before and after. This is another case for the main vessel and its branch. So this algorithm is correct for all these vessels motion. And you can also see the before and after the vessel image quality. You can even see this stenosis after motion correction. Okay. Yeah, so in summary, you can see this slide in the very beginning. So AI and the CT reconstruction, it already married and they, tie with each other quite closely now. And how about tomorrow? I think personally, I think like it will just getting more and more overlap, but doesn't mean we we can do everything in AI, but the overlap will be more. And you can see there's more technology flow from the AI world, for example, the large language model, GPT, whatever. And from the application point of view, the more and more applications from conventional CT will pop up to this area as well. Okay, so in the end, I'd like to thank all my colleagues in Vernon Hills and in Japan. So without their hard work, none of the images here will exist. Thank you very much.
In the interest of time, we will save the discussion, the reception, and move to Lex talk.